We will wait a few more minutes to see if other people are connecting. Yeah, I see there's people connecting right now. So I will just introduce myself and introduce my friend that's gonna do the presentation today. So first of all, thank you for joining us for another Telops Exosens webinar. My name is Marie Lefebvre, and I'm the marketing supervisor at Telops Exosens, and I will be your host for today's sessions. Before we get started, just a few quick notes for you guys. This webinar is being recorded. A link to view and download the recording will be shared with you and will be shared to all registered attendees in a follow-up in the email of the event this week or at the beginning of next week, the latest. We also encourage your questions throughout the presentation. No worries if you want to write it right away. Go ahead. If anything you hear today sparks your interest, you like to have additional clarification, feel free to submit your questions at any time. You can do it at the Demio chat box. It's on the top right of your screen. We'll reserve time at the end of the session to address as many questions as possible live, and remaining questions will be answered in writing in a follow-up email. So you're gonna have all the questions and all the answers in the email. So with that, let's get started with a little poll. So we would like to know what is your experience with infrared thermography. So you should see the poll right now. If you can take a few seconds to answer. Chris, you're muted if you want to add something.
Yeah, hey everybody, we're just looking for, maybe what your experience level is with infrared thermography, or, if you've used it before, or if you have no experience. All answers are fine. Don't worry about it. This just kind of helps us figure out, how we want to be able to communicate with the audience, and in the future, how we want to maybe if we want to change the webinar a little bit so that it's a little more user-friendly or listener-friendly to those who maybe have various ranges of experience with infrared thermography.
Yeah, it looks like we have a few, yeah, most of the people have at least a little bit of experience right now.
Yeah. We can maybe give it 15 more seconds for everybody to answer who are seeing the poll. And okay, thank you guys for answering the questions. Yes, looks like we have a range of people, who have either have experience or do not have experience within infrared thermography, and that's great. We actually like to see a range of people in our webinars. So we can close the poll, I think.
Yep. Thank you so much, Chris, for that. For today's webinar, let me introduce my friend over here. We are pleased to be joined by our field application scientist, Christopher Giesige. Chris has a master's degrees in meteorology, having studied wildfire behavior through infrared thermography. After his wildfire research, he joined Exosens, working with their line of scientific infrared cameras. As a field application scientist, he works mostly with universities and industrial and national laboratories to perform measurement collections, collaborate to improve research efforts, and provide support other various infrared imaging applications. So I will now let the floor to my friend Chris for this webinar. So it's going to be up to you, Chris, with your presentation.
Thank you for that introduction, and welcome everybody to today's webinar, Thermal Response and Mechanical Testing with Low-SWaP IR Cameras. Low-SWaP being size, weight, and power. So today we want to discuss a little bit about some tests and some data acquisitions that we had using two cameras from our Radia family. And we're going to walk you through just a little bit of an analysis that kind of shows their capabilities as thermal cameras, and some information that you're able to derive and some metrics you're able to analyze from those cameras and experimental mechanics applications. To start, a little bit about us. Telops, now Exosens, was founded in 2000 in Quebec City, Canada. now employ over 115 people. So we've grown. Most of these people, including PhD and Masters of Science and engineers, and we take pride in that. We have established ourselves as world leader in thermal infrared imaging solutions. Yes, Telops is now Exosens, but don't worry, you're still the same people, same products. You'll just be seeing the Telops logo a little bit less and the Exosens logo a little bit more. So if you see us walking around at conferences or during webinars and presentations, we will be wearing that and showing that Exosens logo. Okay. So Telops is now just kind of under the Exosens umbrella. So we're making that full transition this year. So don't worry, still the same company. And speaking of our product line, some of our fast IR scientific cameras. The multispectral camera comes with time-resolved multi-channel imaging, a rotating 8-position filter wheel. So you can stack 8 different filters in the wheel and observe the same scene with those different filters simultaneously. Okay, our high dynamic range camera, the HDR M700, able to push those dynamic range limits to see within a single exposure time a temperature range within the same scene of about 900 degrees Celsius. The high performance fast cameras, of course, fastest cameras on the market, are M3K, pushing the 100,000 frames per second window down, of course. And then our Radia cameras. Okay, these are the cameras we'll be focusing on today. Okay, these are small, low swap, again, size, weight, power, more compact cameras that we have, the Radia V60 and the Radia M100, and they're camera OEM modules. We also have our hyperspectral line, pretty well known for our hyperspectral cameras as well, such as the Nano series, the Hypercam that we see over here, but also some single pixel and spatially resolved the Spear series. But then we also have introduced the compact OEM cameras as well. Here are some of our main applications that our cameras are used for. Usually fall under one of these categories: ballistics, combustion, IR signature, gas detection, cold spray, experimental mechanics, which we'll be focusing on today, then additive manufacturing, non-destructive testing or NDT, mineral identification, and fire research. There, of course, are other subsets of applications that we use, but most of our camera users fall within one of these applications here. Within experimental mechanics, our high performance fast cameras are usually a more popular choice. That's because you're dealing with very rapid, dynamic, high energy events, such as ballistic impacts on composite, Hopkinson bar or split Hopkinson bar experiments, or high strain tensile tests. So for these types of applications, when you really need or have the need for speed, you would turn towards our cameras such as the M3K, which in a full window provide 3,000 frames per second, window it down to push 100,000 frames per second, or the M2KUD, that's more spatial resolution, so it's got a bigger focal array, but can still provide 2,000 frames per second in the full window. So those cameras, the faster cameras, tend to be a little bit more popular for these type of applications. But today we want to focus on different types of cameras to show a little bit of versatility within the camera product range to get a sense of how they perform with different experimental mechanics applications as well. Today we're going to focus on our Radia family, okay, the Radia M100 and the Radia V60. These are a line of accessible and ease of use scientific cameras, great for starting out or integration into other systems. Okay, today we'll be talking about their use within experimental mechanics and their data, some data acquisitions, but we do see them for other applications such as industrial R&D, heat transfer phenomena, and then inspection services. But the Radia V60, this is more of your long wave uncooled microbolometer, okay, with an 8 to 14 bandpass and a 12 micron pixel pitch. Okay, it's got a full window of 640 by 480. The max frame rate you'll get out of this is 60 hertz. Several different calibrations that we offer with this camera, standard to extended, somewhere in there. You'll get a calibration between -20 to 400 C. We also offer high temperature thermography up to 1100 C on this, and we might even be extending that coming up here. But we see this camera for more quasi-static events, so more smaller, slower speed tests. Then the Radia M100 is a lot closer to your standard cooled mid-wave camera. We consider it kind of semi-cooled. But this is a targeted 3 to 6 to 4.5 bandpass camera in the mid-wave with a 10 micron pixel pitch. Something unique about this camera is the standard calibration. We don't typically see this in mid-wave cameras, but the standard calibration of 0 to 850 degrees C. And of course, can be extended up to 2500 degrees C for the extended high temperature calibration. And for this camera, see this as more of like a high temperature, high strain rate, high energy type applications. And something also worth noting here with these two cameras is that their spatial resolution is actually pretty good. And we'll get to see that in the images today. But larger focal arrays with smaller pixel pitches will also get you that higher spatial resolution too. To start, we'll be going through a couple of different tensile tests done with the Radia V60 in coordination with the University of Oxford. This upper image here on the left, we can see another one of our field application scientists, Antoine Dumont, will actually be reporting on the great field work that Antoine has done during all of the tests that we'll be looking at today with these two cameras. The bottom image kind of shows us a little bit more of the setup. Okay, we have the V60 here. We can see the close proximity working distance, about 15 centimeter working distance with that. Some optical railing with lights, visible cameras that were used to correlate with IR, and then of course just a TTL triggering system in order to work everything together in sync. The V60 was used at a frame rate of 30 hertz and a 7.5 millimeter lens. Taking a look at the first tensile test here, we're able to visualize this X pattern that develops, indicating the localized plasticity onset. Okay, it has this nuclei right in the center of it, and that's our hot spot, our hot region. And then we have these two bands that develop at a 45-degree axis angle, okay, indicating this type of tension. This one band here, eventually evolves into the dominant band. So we get thermal diffusion afterwards that kind of spreads laterally and vertically from that band itself until we reach a fracture point over here. Something else that's very interesting is if we look down here at this mean temperature plot, we can see that before tension is applied, we have very stable profile. But then right as we initiate some sort of tension, we actually get a little bit of cooling. This is a thermoelastic cooling effect. Okay? Before there's some heating, and then we have the onset of plasticity. This thermoelastic cooling is actually something else that we have been able to identify in other tensile tests. So it kind of goes to show the capabilities of infrared thermography and what we're able to identify with an energy transfer and the thermal profile during these tests. If we take a look at the second tensile test, we can see a set of subsequent images here in A through D and a line profile that we have drawn through the specimen. Okay, that goes from one end all the way through to where the initiation of that localization occurs. That way we can kind of watch over time how that nuclei propagates. So in A, we start to see the nucleation of a hot peak. Okay, this is initiation of plasticity. And underneath it is just a temperature profile. We see that temperature band right here. Okay, a small little gradient between the two, but this is the development. We see right in the center of that is where our hottest point is. If we next look at B, this image over here, that nuclei has started to propagate laterally, okay, to the left, and we see that propagation in the temperature profile. Okay, this hot nuclei band standing strong, it's leaning, right? We're starting to get that propagation. We have a little bit of a gradient leading up to it before we get to the dominant band, and then we can actually see a nice gradient with the tail of that nuclei. And I kind of think of this almost as like a comet, where you have a small gradient in front of the comet itself, and then your strong point, your intense point, is the actual comet, and then we have the tail of the comet. And we can visualize that change in that very subtle change in gradient through that line profile that we've drawn. Okay, so here we have strain localization and thermal diffusion as it propagates laterally. Then if we come to C, right, this is where necking and we get that plateau peak before fracture. It is propagated a little bit further along. And this big spike in temperature here is something that we often see with these types of tests, right? Right before fraction point, we get this huge increase in temperature. You can see from B, it's almost about a 10 degrees Celsius change in temperature. Exactly what we're seeing there and where that's coming from, we're not really too sure yet, but it's an interesting feature that we always tend to see right before fracture. And this D over here, if we transition to D, okay, that is just the thermal profile at the fracture point. Next, this is a little bit further of an analysis, a little closer look at the propagation and some propagation metrics tied to that nuclei that's displacing. Up here on the left, we have this nice little image here that shows the nucleus displacement, or the trajectory of how it is moved. Okay, so we're basically just finding that nucleus, taking the centroid and tracking its movement through time. We can see that it starts here and it is nicely color coded so that uh, areas that are darker red are actually higher in velocity, and then the yellow and the green are lower in velocity. And this ties down here to this plot below it, where we have the dotted red line indicating the velocity movement and the speed of this nuclei. So if we look at the initiation of it, when it first starts to propagate, we actually get a pretty big increase in velocity, say by about 0.65 millimeters per second. And then after that, it kind of starts to tailor off and the speed becomes a little bit more constant. Okay, there's not much movement, maybe a little bit, but not much. And then as we get closer to that fracture point, we have another increase in velocity, followed by a sharp decrease in velocity until it fractures. And we can see the blue line represents the displacement. So the total displacement over the duration of that propagation is about 16 millimeters, before it fractures. So it reached a peak velocity of approximately 0.68 millimeters per second, total displacement of about 16 millimeters. And again, we get that high initial velocity. So it starts off really fast and then it kind of smooths out. Before fracture, you get a momentary increase in velocity and then this large decrease at fracture point. We could even take a quick look at the acceleration, and we're going to get the same story here. There's a big increase in acceleration, and then again, a stabilization of the speed, so it's not really changing too much. And big acceleration, momentary acceleration, followed by a sharp decrease right before the fracture point. So the blue curve is just the raw acceleration data. The red dotted curve is smooth, just so we can kind of see and identify the shape of it. It turns out to have a peak acceleration reached about 0.2 millimeters per second squared. Uh, Again, strong initial acceleration that maintains a more constant velocity. For a split second, we get a big increase in acceleration followed by a sharp decrease in acceleration before the fracture point. In conclusion of these two tensile tests, okay, we were able to identify a few different things. We were able to resolve some interesting thermal patterns and features. We were able to identify some thermoelastic cooling, the onset of plasticity, and we're also able to determine propagation characteristics of localized nuclei and observe how the material behaves before the fracture point. Okay, so next what we'll do is we'll take a look at another test, some compressional loading, again used with the Radia V60, and we'll move on from here. So this is the compression test, also done with the V60 and in coordination with the University of Oxford. And what they did is they made 3D printed materials of different densities of a polyurethane. Uh, Up here, this image on the top left, we can see those different densities. So this one made with 60% of the polyurethane, 40%, and 10%. Visually, we can already tell that there's going to probably be a difference between them, just based upon the geometry and the density of the material itself. This is the experimental setup down here. Okay, we have the compression equipment, loading equipment, and the specimen that is placed beneath it. The V60 this time used a 50 millimeter lens, so a little bit further away, 25 hertz frame rate. So if we look at, we're able to kind of compare how these different densities perform and the thermal response that we get through these different density materials. This is a video showing the compressional loading of the higher density specimen. Okay, it has a higher thermal response, so we get a little bit of a better idea of what that actually looks like through the video of the higher density specimen. And we can see as it undergoes the cyclic compression, the thermal response and the heating that occurs within or throughout the specimen itself. Over here, these are the temperature profiles, okay, maximum temperature and mean temperature. Smooth, the blue curve is 60% of the TPU, the orange curve 40%, and the green curve 10%. And just by looking at these two profiles, okay, so just by looking at these three curves here, 60, 40, and 10, we can already identify that there's a pretty big difference in the thermal response of the different densities. Okay, the 60% is going to produce a lot more heat. It's going to produce a lot stronger heating events and cooling events. Okay, so we have a cyclic pattern where we produce some heating, a little bit of cooling, heating to a peak, cool to a baseline, heat to a peak, cool to a baseline. And we can see that cyclic activity within the profile. The 40% case specimen, it's not as strong, and the 10% specimen, it even looks like it doesn't even heat up at all throughout the experiment. So we'll look at a couple of metrics to kind of help us compare and basically solidify what it is that we're seeing within the temperature profile. We can start with the displacement of the hot region. So if we were to take the different densities and we were just to try and identify where is the heat located, okay, this is more of a global aspect. So we're looking at a hot region, taking the top 25% pixel intensities and drawing an ellipse around them, just to give us an idea of what's going on with the hot region within the different densities. And if we take a look starting with the higher density, okay, the 60% of that polyurethane material, it maintains a pretty centrally located heating, right? And the shape of the ellipses stays relatively the same. So we know that the heating is going to stay more central to this particular specimen. Well, if we transition over to the 40% specimen, we see a little bit different of a story. We see more of a transition as we go down to the lower densities. Where first, within that first cycle, our regional heating is actually in the lower right region of the specimen itself. And then after that, it transitions to become more centrally heated. And that heating, that hot region sits more centrally. But we can also note that it starts to elongate, right? Not like the higher density pattern where the ellipses stay about the same shape. But over here, we see them start to elongate. And then once we get to the lower density material, the hot region actually just kind of sits in the lower right region of the specimen and displaces with a slight downward drift. So we can already tell just by looking at how the hot regions look, like the thermal response of this is going to change pretty drastically from 1% of higher density of the polyurethane to the lower density of the polyurethane. We can also transition to look at just the hottest cluster. So if we were to take, let's say, the top 5 to 10 most intense pixels and find their centroid of them, we can track how that centroid changes and how that cluster how that cluster changes. So we're really tracking the most intense local heating. Uh, Over here at the higher density, okay, higher density, we see that it more closely kind of follows the broader hot region displacement, right? The hottest clusters remain relatively localized. They don't move a lot, maybe at first, but then they all just conglomerate around here in the center, which is, what we would expect. Moving over to the mid-density specimen, it shows a pretty strong displacement from the original localized heating and starts to shift back and forth laterally across cycles. So the hottest pixel cluster is moving quite a bit within the specimen itself. And we see that even more so in the 10% case where there is uh, a pretty good drift from where it starts, where that hot cluster starts to where it ends up. So it starts where we expect, where the ellipse showed us that expect, but then we start to see hotter pixels popping up along this line here, along this displacement line. So the hottest pixels aren't necessarily staying in one place. They're actually moving from here over to here. Um, so from the lower right region more centrally. And again, we get a very different idea when we're looking at the comparison of those three densities. I'll go through now just a couple of plots to kind of help paint the picture and uh, dive into a couple of more metrics here. This would be just heating and cooling. So we're looking at how each of those different density materials heats and how it cools. Okay, and then afterwards we'll look at the recovery aspect of it. So if we're looking at per cycle heating rate, okay, so this is how much it goes from a baseline up to a peak, cools back down, goes back up to the next peak. Okay, it cools back down and then it heats back up to the next peak. And we want to maybe look at, could be important to know how quickly the specimen is heating and how the thermal rise develops during loading. Calculate this, just take the amplitude, okay, so the difference between peak and the previous baseline, and divide that by the amount of time it takes to get from the baseline to the peak. Uh, Again, the 60% dense specimen is the blue curve, 40% the orange curve, and 10% the green curve. This big dip, or these dips that we see from cycle 1 to 2, so from the first cycle to the second cycle, okay, we see this all throughout our plots and throughout our analysis, right? So this indicates there's some sort of an initiation that as soon as it starts to compress for the first time, we actually get some sort of we get something different than what happens throughout the rest of the cycles. Okay, so there's some sort of initiation change that happens before we progress into the other cycles. But overall, the per cycle heating, okay, as we have seen, the 60% specimen, it is going to have a higher heating rate, right? It's actually heating more. We could see that in the temperature plot. It has a bigger jump for each of those. Then the 40% case is a little bit lower of heating events, lighter heating events, and then the 10% density, we barely saw any heating at all. And we saw that in the temperature profile. So that maintains something very, very more of a stable, kind of at the end, we see a little bit of heating there as well. But the 60% case, higher heating rate, okay, and we see that around 0.1 degrees Celsius per second towards the end there. We can also look at how quickly the specimen cools after the peak. So after it reaches a peak and it drops back down to new baseline, that's the cooling period. How quickly does it cool? What is that cooling rate magnitude? Right, a higher magnitude infers that it cools faster and more relaxing. A lower magnitude infers that there's more gradual cooling and relaxation. So down here at the plot, we notice, the 60% specimen has a much larger cooling rate magnitude than the other two do. And this basically just tells us that the 60% cools more rapidly after the peak event, and the 40 and 10% cool more slowly. In the last cycle, there's something that's kind of worth maybe noting here is that the 10% case actually has a larger magnitude than the 40% specimen, which means that even though it has a much smaller amplitude, right, a change between the baseline and the peak, even though it has a much smaller amplitude, it may have a late cycle stronger cooling than the 40% specimen, which implies that the weakest heating event, right, the 10% case has a weaker heating event than the other two, than the 40% and the 60%. So the weakest heating event doesn't necessarily imply the weakest cooling magnitude, which could be something of interest to you. But when looking at heating and cooling, um, as we saw from just the temperature profile right away, the 60% TPU specimen has a higher heating rate and a larger cooling rate magnitude. If we want to understand how these different specimens recover over time, what does it look like when we compare the recovery? We can plot that here, and where we calculate this by just taking the cooling, right? So the cooling event and divide that by the amplitude, and that will give us a recovery fraction. Okay, this is the fraction of the cycle's rise that was recovered from the time you reach the next peak. Uh, 0 recovery fraction indicates that there was no recovery. Okay, so these baselines are very similar, right? There's basically like no drop after the heating event. So we have a 0, which would indicate that there was no recovery in the material. A 1 indicates that there's better recovery near the baseline. So the baselines are closer together, right? So there's better recovery between the two baselines. And it is possible to have a value greater of 1, even though this is a fraction, but that would represent cooling to below the baseline. So we saw with the green temperature profile here, right, it actually almost has a small downward slope. So that's what would give us values greater than 1. The 10% specimen has very small increases in temperature, but the recovery fraction was greater, right? It recovered more because it didn't really have much of a temperature rise. So any sort of recovery will indicate a larger amount of recovery than the other two. For the 40 and the 60% case, we see in these first two cycles, there's actually like no recovery until we get beyond cycle 2, then we start to see some recovery later on in those cycles. Overall, the 60% density specimen had less overall recovery. So even though we see it having bigger drops in larger cooling events, the recovery itself is a lot less because it also had larger heating events. That's what these plots are telling us. So if you want to look at how each performs and how each recovers, say that the 60% will recover a lot less than the 10%. If we want to conclude the compressional loading test, we would conclude that the higher density TPU has greater thermal response, right? More energy is being released in a higher density material, so it's going to have a greater thermal response. The lower density, say the 10% specimen, is more elastic, right? We're able to see that in the plots. And the higher density is more plastic, more deformation. And that concludes the compressional testing. Okay, we'll move on. We've got just one more to cover here, and that will be a first look with the Radia M100, which is relatively new. This is kind of our first look through experimental mechanics using that camera. So we're pretty excited to see what it can do. This is the setup of the last test. Okay, difference. This is an impact test as opposed to the other ones. So again, a 3D printed material. This is a polycarbonate material. And we get a little look at the experimental setup here. We can see why these impact tests are being done in this image down here on the bottom. And then over here on the left is the experimental setup of it. Again, we are using this time the Radia M100. This is that mid-wave cooled camera right? Targeting the 3.6 to 4.15 micrometers. Okay, the big pixel focal array and 10 micron pixel pitch. We'll start with the video of the test itself. You can see here, boom, impact, and then we get the thermal response. The impact occurs on the scale of milliseconds. Okay, the rapid change in temperature happens within tens of milliseconds, right? This is a very high speed event. We're able to determine from this the material geometry and localized temperature fields using the delta T map, right? So taking the post-impact minus the pre-impact, and we're able to quantify a few different metrics of thermal dissipation. Okay, for this test, the M100 was used in was windowed down to 256 by 256, a little bit longer exposure time of 35 milliseconds and a 25 hertz frame rate using a 25 millimeter lens. We continue on with a similar analysis to what we did with the other ones, where we identify hotspots or localized heating, and then we analyze those hotspots. So for this impact test, the image that we see over here, okay, this is our delta T image. This is the uh, post-impact minus pre-impact. We get this nice delta T image from that. And then we look to identify the hotspots within this specimen, okay, because we want to know where those hotspots are, and we want to know how the heating is distributed. Okay, this is going to be more local. So what we're doing is we set a threshold for this. Okay, the hotspots are determined by setting this threshold, say the top 2% pixels, because we only want to identify the um, the peak of the hot spots, right? We want to reduce any small temperature fluctuations. We want to reduce any fluctuations due to noise. So we threshold this in order to identify only those peak hot spots that are within the geometry. And the smaller image over here is just those hot spots that were identified. This is a more of a spatial analysis, different metrics for a hotspot and resolution. There might be a few other metrics that you're able to identify, but we just did something simple here to kind of show the capabilities of what can be done, using this camera. So the number of hotspots detected 26. Okay, we were able to identify how thermal energy is distributed within the specimen, knowing that a lot of these are more local and not as global. Okay, there was a max delta T, so the strongest thermal rise after impact was about 3 degrees Celsius. And something we didn't do here, but you could, is you could map out exactly which of those hottest hot spots, where they are located. So you could see where that hottest heating is taking place. The median hotspot area, 19 pixels, total hotspot area of 606 pixels. And then we can also calculate the localized area fraction. This would just be what percent of the material is occupied by these hotspots. We can see here that is 1.2%. So we're able to characterize some cool hotspot metrics, and see again what's going on with localized heating of this material. We can again also look at the recovery of the specimen, recovery of the material after impact. So if we start by looking at the temperature profile, we can see that the sharp rise in temperature is right after the impact occurs. Okay, the specimen exhibits a rapid temperature increase. Okay, the red dotted line is where that peak temperature is reached before we see a gradual cooling exhibited by this cooling curve right here. We could take a closer, deeper look into the cooling after impact, or the cooling after the peak temperature is reached. So this is the cooling rate. This plot next to it is the cooling rate after it reaches this peak temperature, okay, this red dotted line. And we can see that there's a pretty strong magnitude when it first starts to cool, and then it kind of steadily declines back to an equilibrium point, back to zero, this red dotted line here. If you wanted to look a little bit further, you could analyze, different points to actually determine the magnitude of, the cooling itself. But overall, the general behavior, we see that there's a rapid increase in temperature after the impact that kind of produces a strong thermal gradient within the material. And then that thermal gradient initiates some sort of a steep cooling magnitude, okay, followed by the slower decline. If you were to look specifically at the magnitude, you could find the cooling rates at different points along this curve, but just kind of took the average cooling rate here to see that it is about 0.21 degrees Celsius per second. So in terms of recovery, this material on average will cool at about 0.21 degrees Celsius per second. After the impact occurs, the time it takes for it to reach peak temperature is about 1.32 seconds. So it reaches peak temperature fairly quickly before it starts to cool again. And to conclude this test, what we were able to do, seeing these first images, the M100 was really nice. We were able to perform an analysis from some pre and post impact, all right, derive our delta T. And then through hotspot segmentation, we could identify the hotspot characteristics and metrics for those. And at the end, we were able to quantify impact thermal response via temperature increase, and then look at the recovery and see how this material recovers. So thank you for bearing with me during this webinar. I know there's a lot of information there and analysis of several different tests, but really just wanted to gain an understanding and idea of how we can use these cameras in order to resolve, what's going on thermally within different materials and different experimental mechanics applications. So infrared cameras, they're great tools to incorporate into experimental mechanics. Okay, it can help map thermal fields, achieve thermomechanical responses, and give us a better in-process understanding of thermoelasticity. We did multiple tests. Okay, these were carried out with the V60 and the M100. They are Low-SWaP cameras, and we were able to observe some thermoelastic cooling and heating, onsets of plasticity, evolution of strain localization, and thermal diffusion. We're also able to see how heat displacement occurs in recovery metrics under loading, and we're able to identify, hotspots, how heat is distributed globally or locally through different materials. And you can look at the post-impact recovery. So how these materials are recovery after undergoing some sort of loading event. Okay? And these Low-SWaP cameras, we think they're going to be nice and easily integratable into multi-camera systems, or very integratable and easy to use within DIC systems themselves. Sometimes they can be challenging with bigger, bulkier cameras, but we think these two smaller compact cameras are going to have a lot of use for that. All right, we'll save some time for some questions. I'll stick around. We'll try and get to as many as we can. Any that we're unable to get to, I will follow up and provide written answers to afterwards. All right, thanks again.
Thank you so much, Chris, for this presentation. I think Chris received a few questions already on his side. If you have one, feel free to write it in the comment box at the top right of your screen. There is a chat place where you can write your questions. If we don't get to your questions though right now, keep an eye on your inbox for our follow-up email, which will contain written responses to all the questions we're going to have today. So Chris, would you please begin with the first question you have?
Yeah, so let's see. The first question here, we have what is the max frame rate of the M100? Yeah, so the M100 again was the mid-wave camera, the smaller mid-wave camera that has higher frame rates, performs a little bit more like your cooled mid-wave infrared camera. And in the full window, it's full window, again, 180 hertz, but you're able to window that down. And if you window it down to something, say, like a 128 by an 8 sub window, so that's pretty small, I know, but you can achieve up to about 1,000 hertz with that. So that camera, yeah, so that's why we see that being able to be used for some higher strain, maybe more rapid, higher energy events. Let's see. Second question, we have it. The spike in temperature during the tensile test. You mentioned that you don't really know what it is. Do you have any guesses, or is there anything that you think it could be? Is it something physical? Yeah, that's a good question. Actually, something I was just discussing recently with somebody not too long ago. Originally, I kind of thought, all right, well, it is physical. It starts to, right before it fractures, it actually heats up a lot. And that kind of made a little bit of sense to me. But then the question was, well, are we actually seeing heating underneath? So once it starts to fracture and we get, say, a crack or something in the material, are we really just seeing the thermal response from inside the material itself instead of what we were originally seeing on the surface? So we get that big spike or that big increase in temperature. And that is a good question. So, I always thought it was the surface response that we were seeing, but it's possible that we're actually seeing something else happen. So not too sure there, but that was my guess originally.
And do you have a last one,
Okay, I
or?
don't see. Yeah, let's see. I think that is it for now. That is all we have.
All right. So thank you for attending today's webinar. Feel free to write us an email if you have more questions, no worries. If you are around Norfolk, Virginia from June 1st to the 4th, by the way, join Chris alongside our business development manager, James Garner at SEM. You will find us at booth 105. So we will be able to chat with you, answer all your questions and more. So we are welcoming you at our booth at SEM. And like I said earlier, keep an eye on your inbox for all the answers of your questions and details. Thank you so much, Chris, again for this presentation. And see you soon for another webinar. Have a great
All
day.
right. Thank you, everybody.